So with Euclid, as you guys probably found when you were looking online, depending upon your source, your information may vary a little. We don't have a lot of written historical record of him, so we don't know exactly when he was born. We don't know exactly when he died, but we have approximate dates. So your answer for when he lived might be slightly different than the person next to you. I'm going to go and pull up the answers that I have, and we'll talk about it, and I'll tell you specifically which ones to make sure you have the exact same thing as opposed to a general idea. So let me go and pull that up. Okay, so everyone should have the same thing for known as the father of geometry. Now, number 2, when approximately did Euclid live? What I've got written down is about 325 to 265 BC. As long as yours is somewhere within the range of the 300 to 200-ish BC area, you're good. If I were to ask about this on a quiz or a test, if you had somewhere around there, you're fine. If you said like 500 to 600 BC, then I would say that's a little too far off. So somewhere within the 300-ish, 200-ish range is about when he lived. Now, he grew up in Greece, and question 4 might have been kind of difficult for you to find. That was kind of something you had to infer. This was significant because that meant he was able to go to school. So because of where he grew up, it was an affluential enough area that he was able to go to school and thus get the instruction that led to him being able to have the knowledge to do what he did with geometry. Okay, so for number 4, it was significant because he was able to go to school. Now, he studied under Plato. And Plato, as you know, was also a philosopher. He was also a mathematician. So back when I took my history of mathematics class, what I realized is a lot of these mathematicians were also philosophers and also astronomers. A lot of times they overlapped with that. As an adult, he lived in Egypt. So he taught at the University of Alexandria, which is in Egypt. So that might help you kind of piece that together. He grew up in Greece, but as an adult, he taught in Alexandria, so he lived in Egypt. So the country's Egypt, the university, the place was Alexandria. And everyone should have the same answer for number 8. His famous book is The Elements. So I have a little article about information more about Euclid, and hopefully they're in a stinger where I can tell you more about it. But for sake of time, I'm just going to stick to the basics here. But basically, Euclid, so the rules, the statements of geometry were true even before Euclid realized it. For example, one of the statements is that through any 2 points, there is exactly one line. This was true long before Euclid was even alive, right? That was true before he even recognized it. What Euclid did is that he recognized and discovered these rules of geometry. Kind of like 1 + 1 is 2. That was true before you were even born, right? But then at some point you realized and recognized 1 + 1 is 2. So he discovered geometry, and then not only did he discover it, but he put it in a nice format. So he went through and defined things. He put definitions to things. He wrote out these statements called postulates and theorems and put it into a nice, logical, organized format, and that is what his book, The Elements, is about. Now, number 9, we remember him today mainly because he wrote the course of geometry. So his book, The Elements, is basically what we use for geometry. Now, of course, we take it to modern-day English and high school level, geometry level. But his book, The Elements, is basically the foundation for our high school geometry class. So just a reminder, number 10 here, we talked about this with our vocab last time. Postulates, or also known as axioms, these are statements that cannot be proven, but we do accept them as true. So we agree they are true, but they're so basic we cannot prove them as true. And then number 11, I love the different answers for this. We wrote Barnes & Noble or Amazon or eBay. Yes, you can purchase it there. The idea we were going for was that the revised version, so his Elements has been kind of revised for our high school geometry. So the Elements is like the golden book for geometry, right? But if you were to open up the Elements and read it, it's going to be a little higher level. So I haven't, but the textbook company people have taken geometry and kind of put it at our high school level. So his revised version is our high school geometry textbook. But yes, you can purchase it on Amazon. That's where my husband got his copy of The Elements. I'm sure Barnes & Noble also has it. Who knows? Maybe eBay too. Okay, so you do want to know these basic facts about Euclid. Again, for the dates of when he lived, somewhere in the 300s to somewhere in the 200s. You could say 318 to 296, and I'll kind of get somewhere in there. Okay, questions with some of our beginning stuff here, the top half of our picture. So if you need to adjust things on your paper, go ahead and do so. Now, the 5 postulates of Euclid, there are a lot of postulates, so you might have had some, depending on your source, again, they might have had a different beginning postulate, or they might have phrased it differently. So I'll go and show you the 5 that I had. If you have something different, don't worry about it. You don't need to change it. Today on our notes, I've given you the 5 that we used for our starting point in high school geometry. So don't feel like you need to change and adjust the bottom half here. So again, some of this has been adjusted to make it at our level for high school geometry. So our first one, any 2 points form a straight line. That's what I just drew up there. We've already kind of talked about that. So for any 2 points, there's exactly 1 line. Our second one here, an infinite number of lines can be drawn through 1 point. So I've got 1 point, I can draw infinite lines. Number 3 talks about circles. So a circle can be drawn with a point and a radius. The point is our center, radius is that distance from the center. Unit 9, I think it's 9, is when we do our unit on circles. There's actually a ton of statements, lots of theories and cautions within circles. So it's really interesting, a lot of the connections between the circles. All right, statement 4 here, postulate 4, all right angles are congruent. We'll talk more about that later today. And then parallel postulate, again, usually the phrasing is quite a bit different. So I'll show you what I've got here and explain through it. Now the parallel postulate says, all right, we've got a straight line, which a line has been defined as straight set points. And we have a point that's not on this line. There is one and only one line we can draw through here that will be parallel. So there's one and only one that we can draw through that point that will be parallel. So that's our parallel postulate. And again, keep in mind we're dealing with flat surface, plane geometry, Euclidean geometry, Euclid, that's what I mean. So again, if you have something different, don't worry about it. There are a lot of postulates, and so depending on your source, they might have had a different beginning of 5 postulates, and they might have phrased things separately. But these are just ones I have here. All right, any questions with this? Awesome. Okay, so let's go ahead and check our homework next. So EB and BE, those are 2 different ways to name the line. Same line though. So answers would vary just as long as you have any 2 points on the line with a line over top, doesn't matter the order. And then same idea for number 9. For a plane, we only need 3 letters, 3 points that are on the plane, so any 3 of those points on there. Now, I do want to draw your attention to our picture there. So we talked about how with angles, sometimes they'll put a number in it, and we can call it angle 1 or angle 2. Now, they do a similar thing with lines and planes. You'll see on the picture that there's a plane, or sorry, the line, there's a lowercase n and a lowercase n. That allows us to call it line N or line M. We use lowercase letters to denote that. A lot of times they're written in cursive, so just a heads up with that. And then you notice that they call it plane C. So you can see that C is on the plane, it's like the letter, but there's no point for it, so it's not a point on the plane. They're just, again, if the picture has a letter like that where there's no point next to it, you can just call it plane C. It's not often that we'll do that. We'll usually use the 3 letters for it. Okay. Do you have questions on 8, 9, 10, or 11? First, jump there with that first question. I'm going to scroll up. Now for number 12, it says to name the segments, because for segments, it doesn't matter if we go RS or SR, it listed the options. So you don't have to have both here, because it just said to name the segments, not listed all the possible ways. So you should have 1, 2, 3, 4, 5, 6 segments. Or it's like RS, RT, RW, ST, SW, TW. To make sure you have proper notation of the segment over top rather than for 13 though, because it says to name the rays, it is going to be different if you have the letters in a different order, right? Ray RS and ray SR are two completely different rays. They have a different starting point and they go in different directions. So you should have, what is that, 2, 6, 8, 10, 12 of those. Alright, so 12 through 14, there's quite a bit for you to check there. But do we have any questions for 12 through 14? Again, a lot of this beginning geometry stuff is pretty tedious because it's just very basic foundation stuff. Alright, go ahead and check your answers for 15 through 22. And then again, keep in mind, so 19 through 22, for planes, we only need 3 letters, 3 of the 4 letters. So I went ahead and listed the 4th letter. I'm going to write it out a little bit better for you. You don't need all 4, just any 3 of these 4. I just wanted to go ahead and list them for you. So if you had plane TQX, you would know that it's still the correct answer. So again, any 3 of the 4 letters. Yes. Number 14. Scroll back. Alright, so we have questions on 14 through 18. I'll go and scroll up to those in the back there trying to crank their neck around. Alright, any questions on what we have here? Okay, so in the next chunk, we've got 27, 29, and 31. And then 33 through 36. I want to draw our attention to numbers 34 and 36. 34 and 36. 34 says 2 points that are non-collinear and 3 points that are non-coplanar for number 36. So I had a student ask me about this last class. So collinear means that you can draw a line through it, right? Non-collinear means you can't draw one line through all the points. So when it asks if it's possible to have 2 points that are non-collinear, this is not possible because any 2 points, I can draw one line. But she was getting a little confused with it that she had, okay, here's a point here on that line, here's a point over here on this line. So she's saying, well, those aren't collinear because they're not on the same line. But it's not, is it on the same line in your picture? The question is, can I draw one line through both of them? And indeed I can, okay? So I want to make that distinction there. It's not just, oh, well, I drew them so they're in separate lines. Collinear or non-collinear would be, can I draw one line containing both of them or not? Okay. So same idea with our plane. So it said 3 points. Okay, I remember 3 points that are non-coplanar. 3 points that are non-coplanar. Okay, so again, she was thinking, okay, well, I kind of use a cube shape. All right, we'll just go with that. She's like, well, I've got a point here, I've got a point up here, I've got a point down here. Those points are on 3 different planes, so it's not coplanar. Well, again, coplanar is, can I draw one plane through all 3 points? Non-coplanar would be, I cannot draw one plane through all 3 points. And so it's not possible through any 3 points I can draw one plane. So again, because I always draw on a plane, let me go and take a point off the plane. So here I've got 2 points. Let me throw a third one. I can draw a plane through those 3 points. So the question is, can I draw one plane that contains all 3 points? Yep, it would slice right through that cube there. So again, it's not, can you draw me a picture where it looks like, or that they are on 3 different planes? The question is, can you draw one plane containing all 3 of them? Okay, so that's the difference between the non-collinear, non-coplanar. All right, questions with our chunk up here? Yes.
Wait, so if there's like, if it's only 2 points on like 2 different planes, can it still intersect or whatever?
So if I have 2 points, let's say let's say this point down here, and let's just go to the corner of the light there. Those are 2 different planes, right? The question is, can I draw one plane containing both of them? Yeah, I could. I'm going to use my clipboard because it's smaller, but I could draw a plane here where it starts and goes up and hits the next wall. So they would be coplanar. So basically, any 2 points would be coplanar. Any 3 points would be coplanar. Once you throw in a 4th one, 3 is what establishes the plane. So let's just go ahead and do the 3 on the board here. That our plane is this guy here. If I try to put in a 4th one, I can't draw a plane that contains those 3 and then scoops to get the 4th. Does that make sense? Because it's no longer a plane. It's no longer a flat surface. Other questions with that? Okay, awesome. Okay, so that was just a little more continuation of our vocab from last class. Let's go ahead and take a look at our notes for today. You can tuck those textbooks away. All right. Is there one that did not put the notes? Okay. So on our vocab sheet, we had second edition postulate, Euclid edition postulate. We briefly talked about this last class. Now we'll actually define what it is. So keep in mind, a postulate is a statement that we cannot prove, but we all agree and accept it as true. So it's a fact, but it's just so our segment addition postulate and angle addition postulate. Key thing for segment addition is that these points are collinear. So I'm going to write collinear points, which means we can draw a line through them. And so when we have a set of collinear points, as we see here with our picture, then basically I say the pieces can add up to be the whole thing. So for example, the measure of angle AB, not angle, this is a segment, the measure of segment AB, and if I add to that the measure of segment BC, guess what that's going to equal? The measure of segment AC. Now notice we're talking about measures here, so I have proper notation. There is no segment on top, right, because we're talking about the measure of it. And we have an equal sign, because we're talking about the measure. All right, now sometimes, so this is the big idea here, sometimes you'll see this written in a slightly different format. let's say, for example, I subtract my AB over. Would you agree that BC is the same thing as taking the whole thing and subtracting away AB? So sometimes you might see it written like that, where instead of having the pieces add to be the whole, it'll say a piece equals the whole minus the other piece. This isn't as common. When you see that, we still call it segment addition postulate because it is just a variation of it. Technically, it's segment addition postulate with subtraction property of equality, but we'll just call it segment addition postulate. Don't call it segment subtraction postulate. It's still segment addition postulate, just with that subtraction property of equality. But again, for the most part, we will see it written where it's the pieces that have to be the whole thing. Now, this doesn't have to only be two pieces. I could, if I threw a third one here, it's called a B. I could say AB plus BD plus DC equals AC, right? So it's not limited to just two pieces. So it seems pretty basic, common sense. That's why it's a postulate, right? It's pretty basic. We agree that it's true. All right, angle addition postulate. This is for adjacent angles. Adjacent angles. I'm sorry, right here, for some reason, my smartboard squiggles like a wet noodle. So that says adjacent, although it's hard to read. Let me try that again. Adjacent angles. Okay, what does it mean to be adjacent again? Next to each other, they share a side. All right, so we have adjacent angles here, and what this says is if I have adjacent angles, I can add the pieces up to give me the whole angle. So the measure of angle 1 plus the measure of angle 2 equals the whole thing. Now, in order to talk about this entire angle, I'm going to have to use the three letters A, B, C. I can't say 1 plus 2. We can't call it like angle 3 because it's not labeled as angle 3. We have to use the three letters. So measure of angle ABC. Or you could have said CB. If you really wanted to, instead of saying angle 1 and angle 2, you could have said measure of angle ABD plus measure of angle DBC equals measure of angle ABC. But the whole purpose for putting the numbers there is you don't have to write as much. Notice again, we're talking about measures equal. It's the beginning. And just like with our segment addition postulate, we could subtract away a piece and say the piece equals the whole minus the other piece. Same idea. Okay. Questions with those two postulates? We'll get into more with it later. So now let's talk about the beginning postulates of geometry for our high school geometry class. Okay. So these are slightly different than Euclid's original postulates. Again, they've been adjusted for our high school geometry. So these are the 5 that are kind of our starting building blocks for high school geometry that we're going to use. Our first postulate, we've already talked about this, through any 2 points, there is exactly one line. Pretend that went through that point. Let me just make it a little bigger. Okay. Our second one, if 2 distinct, meaning different lines intersect. So if we have 2 lines intersecting, they intersect in exactly 1 point. So again, this is very basic. Can't prove it, but we all agree that is a true statement. All right, postulate 3, if 2 distinct planes intersect, then they intersect in exactly 1 line. I always have a hard time drawing this, so I'm just going to refresh your memory. Think ceiling and front wall, and they intersect along that edge, that line there. I'll give it a shot at drawing this. Okay. Something like this. Here's one plane. Go with green instead. Here's another plane. Ooh, I don't want that to beat up or anything. That's behind it. I think that means that the red should now be dotted. you that are artistic. Lucky you. Okay, so these two planes are intersecting right along this line. I think it's a lot easier to just take your hands to the Vulcan and put it together. So we've got two planes intersecting that intersect along that line there. I had a professor in college, so one of the courses I had to take for my math degree was called Modern Geometry. Dr. Mamega, he was wonderful. I loved him. Very happy guy. And he would be, I mean, there were some pretty complex things we were talking about, and he'd be drawing, and you'd look, and you're like, I don't know what in the world it is you're doing, and all of a sudden, you're like, whoa, it all came together. My drawings will not be like that. I am not artistic. But there's my attempt at it. So we've got two planes intersecting. They intersect along that line. Again, just take ceiling, front wall, the edge of the classroom. All right, postulate 4. Through any three non-collinear points, there's exactly one plane. Again, we've already talked about this. We've got three keyword non-collinear points. Only one plane can be drawn through those. So, I mean, it's just like you use your paper as a plane. Only one plane can be drawn through those. I can't draw a separate plane that contains those. If they were collinear, that means that they're on the line, then there would be infinite planes to be drawn through. Okay, so then we'll talk about postulate 5 in just a moment. Our first 4 postulates here, these are like the most basic, literally the starting point for geometry. We're talking about points, lines, and planes. Now, for the rest of geometry, we're then going to build up and talk about parallel and perpendicular lines. And when we draw a line through parallel lines, what happens? What characteristics, what relationships are made? So we talk about congruent triangles, similar triangles. Again, what relationships are made there? We move on to quadrilaterals, polygons. We then have circles, and then we have our 3D shapes for surface area and volume. So right now we're talking about very, very, very basic stuff. These beginning postulates, will we be using these very often? No, because we're going to be talking about bigger things, like triangles, you know, when 3 lines come together. But we have to start off somewhere. So we start off with the most basic stuff, and then we build upon that. Now, our 5th postulate down here, our linear pair postulate, this is something that reappears the entire year. Almost every single unit, the linear pair postulate is back up. So this one, it's probably good if we go ahead and refresh our memory as to what a linear pair is. Who can recall, let me grab I should be practicing names, I apologize, I've not been. Who can recall what a linear pair is? Joseph.
Points that are on the same line.
So that's going to be collinear. You've got the right wording there, linear. Linear pair, though, is something different. Linear pair. Laura? Good work finding that vocab sheet and reading the definition. 2 adjacent angles whose non-common side forms opposite rates. Let's translate that. What does adjacent mean? There's 2. Go next to each other, they share a side. So there's one angle. They're going to share this side. Their non-common side forms opposite rates, so I need an opposite ray. So angles 1 and 2 here are a linear pair. Okay? So they're adjacent, they form the opposite rates. So what conclusion can we say? And we talked about this last class, but we're just going to keep ingraining it into our brains. What conclusion can we say about 1 and 2?
But the sum of the measures of their angles will add up to 180 degrees.
Good. Their angles add up to 180. What do we call that?
Supplementary.
Supplementary. So that's what our linear pair postulate is. A linear pair postulate simply says 2 angles form a linear pair, and then they're supplementary. So it just simply says linear pairs are supplementary. Okay. Now this is a one-way street. It's an if-then statement. We'll talk about if-then statements more next unit. That's an if-then statement. If they're a linear pair, then they're supplementary. So what that means is linear pair automatically means supplementary. But just because it's supplementary does not automatically mean linear pair, right? Okay. Thank you, 3 of you, for your input. Good work going back to that vocab sheet. If you don't know, guys, find the vocab sheet and look at it. That's how we learn it. Very good. Okay. So if it forms linear pair, then they're supplementary. Now notice there's something also distinct about this, is that it actually has a title, linear pair postulate. These other ones just say postulate 1, 2, 3, 4, 5. When it has a title, we can call it by that title. So when we do proofs, you're going to have to give a reason for why you make the statement you make, and that reason would be linear pair postulate. If you remember that title, you can go write out the title. You don't have to write out the whole thing. If you forget the title, just write out what it says. Linear pairs are supplementary. Now, not all postulates and theorems have titles. Okay, so as you can see, the ones above, they don't have titles. When there's not a title, you can't just call it postulate 1, postulate 5, theorem 14.6, because depending upon the textbook, they order them in a slightly different order. So theorem 14.6 here was not the same theorem 14.6 in my high school textbook. That was made back in the 70s. I was not alive in the 70s, but my textbook was from the 70s, okay? So theorem 14.6 is not the same across the world. Ignore that. It is not a black day. You're stuck with me for more time. But linear pair postulate, that title, that is the same across the world, okay? So we're not going to be saying the numbers. In fact, we won't be giving numbers. We'll just say it's a theorem or it's a postulate. So if there is a title and you remember the title, great. Use it. Save yourself some handwriting. But if there's no title, you have to write it out. Okay? And if you forget, then just write it out. You know what it says. You know that linear pair is supplementary. Just write it. All right, so this is a key one. Put a star next to it, highlight it, do something to make this stand out to you. That is one that you want to have memorized for the rest of this year. Okay, so those are our beginning postulates. Everything else builds from there. Now we do have some additional postulates, so those are kind of the starting points. Let's go flip it over to the back side. And here are theorems. Okay, so our first one is the right angle congruence theorem. It's a pretty basic theorem, and it simply says all right angles are congruent. All right angles are congruent. Congruent just simply means they have the same measure. Would you guys agree that all right angles have the same measure? Yeah. So this is a theorem. This is something that we can prove. We have the definition of right angle, says this measure whose an angle whose measure is 90 degrees. So I can have angle 1 and angle 2 are right angles. By definition of right angles, the measure of angle 1 equals the measure of angle 2. Measure of angle 1 equals 90 degrees, measure of angle 2 equals 90 degrees. Then some substitution, I can say measure of angle 1 equals measure of angle 2 is 90 equals 90. And then I can say since the measures are equal, they are congruent. That was like a 4 or 5 step proof right there, right? Suppose you forget this theorem, you can go ahead and prove it within your proof. But if you remember the theorem, it's a lot easier to say, hey, by the right angle congruence theorem, I know all right angles are congruent. Saves you time. Okay, so that looks pretty obvious. Now the congruent supplements and congruent complements theorem. These two theorems are very similar in the wording as well as obviously the title. What do you think supplements is talking about?
Supplementary angle.
Supplementary. So like if I said angle 1's supplement is equal to, what that means is that 1 and 2 are supplementary. Same idea with complements. It's complementary. This one is the more common of the two. We have supplementary angles pop up a whole lot more than our complementary angles. Now, every year I have students that forget about this theorem, and it's fine. You just have to, again, have an additional 4 or 5 steps to prove it. So if you remember this theorem, it can definitely save you some time and length in your proofs. So our congruent supplements theorem says if two angles are supplementary to the same angle, two angles are supplementary to the same angle, then those two angles are congruent. So if two angles are supplementary to the same angle, then those two angles are congruent. I'm going to use that congruent symbol again to prove it. So let's talk about what this is saying. Let's just go and draw a picture to illustrate this. Two angles are supplementary to the same angle. So let's go ahead and just off this side. I'm going to draw an angle here. And let's go ahead and draw an angle that looks like it's supplementary and another one looks like it's supplementary. Alright, I'm just going to call this angles 1, 2. So suppose I come along and tell you, hey, guess what? Angles 1 and 3 are supplementary, as are angles 2 and 3. Okay, so that's two angles are supplementary to the same angle. Alright, so let's talk about the math behind this. So if 1 and 3 are supplementary, I like to use the easy one. Let's say this is 100 degrees and this is 80 degrees, right? Would you agree that would mean that they're supplementary, right? Okay. So 1 and 3 are supplementary, and I also know 2 and 3 are supplementary. So if 3 is 100, how much must 2 be? 80. So what this says is, in that situation, 1 and 2 would have to be congruent, which makes sense. They've got the same measure, right? So the idea here is that they add up to be 180 both times, right? And angle 3 didn't change magically between the two angles. So if it adds up to be the same amount, and 3 is the same amount, then 1 and 2 have to be the same amount. Okay. So that's called congruent supplements theorem. Again, a really important one to remember saves you time on proofs. Congruent complements theorem is the exact same idea, just with complementary. If two angles are complementary to the same angle, then those two angles are congruent. So we'll write that out. If two angles are complementary, you're so nice. Two angles are complementary to the same angle. Then those two angles are congruent. I'm going to use that angle notation. You'll see me use this. An angle symbol with apostrophe S for meaning angles. Just for sake. So if two angles are complementary to the same angle, then those two angles are congruent. Exact same idea, just they have to be 90, so that would be 90. Okay. Questions on our right angle congruence? There's supplements for congruent complements. Awesome. Okay, so our vertical angles theorem. This is a biggie. Go ahead and put a star next to it, highlight it something. You definitely want to know this. Big. Alright. Vertical angles theorem. Now, it's again good for us to recall the definition of vertical angles. So who can recall or find their vocab sheet that has it? What are vertical angles? I love hearing the flipping of pages to find our vocab sheet. This is good. Yes.
Angles whose sides form opposite rays.
Good. Two angles whose sides form opposite rays. Opposite rays look like a line. So we basically have that X. That's the X shape we're looking at, right? So this is a really important distinction to make. The definition of vertical angles, notice what it was. It just simply told me what vertical angles are. What do they look like? Okay. So definition only lets me look at this picture and say, hey, angles 1 and 2 are vertical angles. By definition of vertical angles, that's all I can make. The vertical angles theorem gives us more about it. The vertical angles theorem says vertical angles are congruent. So it's the theorem that tells me that they are congruent. Every year I have students that try saying by definition vertical angles are congruent. Now the definition says nothing about congruent. Definition simply says those are vertical angles. Once we've established their vertical angles, then I can state in my proof angles 1 and 2 are congruent by the vertical angles theorem. Okay. So it's really important to know the difference between the theorem and the definition. If in a proof, when we get to proofs, you're not sure whether it was a definition or theorem, then just write out what the theorem says. You know vertical angles are congruent, so just write that out and don't get it wrong. Okay? So vertical angles are congruent. We can again go through proving this. I believe we would use linear pair with the congruent supplements theorem. But we have that notation, and that part indicate that they're congruent. And keep in mind that this other set of angles here, those are also vertical angles, those would also be congruent. Okay, so that's another one of our biggies. Linear pair postulate, vertical angles theorem, those are the two biggest postulates and theorems from Unit 1 that carries over the rest of the year. These other ones you'll see throughout the year, but those are the two biggest things. Okay, so next up we have a couple of definitions. Definition of congruent segments, definition of congruent angles. Same idea, one's with segments, one with angles. Okay. So congruent segments, the definition is congruent segments have equal measures. Congruent segments have equal measures. Now, the way that I've phrased this definition, it's kind of hidden that this is actually a biconditional statement. What biconditional statement means is it's true both ways. So we'll learn more about biconditional, conditional, contrapositive, inverse, converse, all that next unit. Next unit's our logic and reasoning unit. But what a biconditional statement is when we have the words if and only if. So if I were to write this as a biconditional, two segments are congruent if and only if they have equal measures. What that means is it's true both ways. So if I have two segments that are congruent, I know that means they have equal measures. If I have two segments that have equal measures, I know that means they are congruent. So what that means is we can go both ways with it. Okay? So that's helpful for us in proofs. Basically what this translates to is if I have two segments that are congruent, I can say segment AB is congruent to segment CD. If I know that, then I can go ahead and draw the conclusion that the measure of segment AB equals the measure of segment CD. So if I know they're congruent, I can then say by definition of congruent segments, their measures are equal. Likewise, if I start off with their measures are equal, then I can go back and say they are congruent. This arrow, this double arrow, that's what we use to indicate it's a biconditional. Definitions are actually biconditional segments always. Just might not be written in a way that you can see it like that. Alright, so same idea with congruent, definition of congruent angles. So congruent angles have equal measures. Congruent angles have equal measures. And again, make sure you use proper notation. For angles, if we're talking about those figures, we would say angle 1 is congruent to angle 2. But when we're talking about their measures being equal, that's when we have to put that little m in front. So the measure of angle 1 equals the measure of angle 2. And again, this is true both ways. Alright, we use this definition of congruent segments or angles a fair amount in our proofs, more so in the beginning than toward the end. Okay, questions with that? Awesome. So what I would like for us to do now is our homework is a relatively lengthy homework because I want to use some of it in class for like practice to kind of model these. Our homework is basically taking these concepts and now applying them to actual pictures. So before I pass them, I'm going to take a look at your assignment sheet so you see what's coming up. Always refer back to your assignment sheet. Homework, so you see today, we've covered our Euclid, postulates, segment, angle-ish, postulate, and obviously some other stuff as well. Your homework tonight is lesson 3 homework, I believe it says. Now, what is happening next? Class. Good. So our second quiz. So our first quiz that was over our algebra stuff. Our second quiz is actually over our geometry stuff. Woo, we get to learn geometry and quiz over it. So what we've learned last class, so last couple classes like our vocabulary, our terms, linear pairs, vertical angles, what we learned today with our Euclid information, the top half of our sheet with those facts. You don't need to worry about the bottom half. The top half of those facts, and then what we learned today with like segment and angle addition postulates. That's what's going to be on your quiz. It's a shorter quiz, just one page front side. So that's what we have next class. Now your quiz is from last class. So anytime that this year I have 4 sections of geometry honors. It's about 126 kids in class. So anytime geometry honors takes any assessment, that means I immediately have at least 126 papers front and back to grade, which takes me more than class grade. So usually quizzes, it takes me about a week to get back to. Tests usually 2 to 3 weeks. So just keep that in mind. Ideally, I'll have your quizzes for you next class, the quiz one, but it'll probably be 2 classes. What's your question? Next week or just next class? Next class. So you'll just, when the following class, you'll just make up the quiz time when you come back. Okay, I'm sorry, I was counting and talking at the same time, so let me know if I gave too many papers or not enough. Let me pull up. All right, is there anyone that did not get the homework? Okay. So again, you can see this is a lengthier one. We're going to go ahead and do some of it together. Now it's really like classwork / homework, but to finish it is for now. So as you look here, you'll see there's segments, there's angles. It's really a lot of application of what we've learned the last couple of days. Now I want to go ahead. The first 5 are really simple. It's just numbers. You're adding, subtracting. But let's go take a look at number 6. Here we have a segment, and I want to redraw our attention to this notation here. What does this notation let us know about the picture? I think I heard someone say something. Yeah, so this means that they're congruent, which means their measures are equal, right? If I have 2 tick marks, like we see further down for number 9, I think it is, then those would match up. So notice in our instructions, it doesn't tell us, hey, segment ST is congruent segment TU. You look at the picture and gather that from the picture. Okay? So if they're congruent, that means their measures are equal. So for 6, it says, what is the value of ST? Well, all they've given us is an expression for ST and an expression for TU. How in the world am I supposed to actually find the number value for ST? Thanks. Yeah. Perfect. So what you'll notice is that, again, we use algebra throughout all of geometry. But what we do is we have to take these geometry concepts. They're not giving us an equation. So not wrong, we gave you an equation that solve for x, right? They're not giving you an equation. They give you expressions. You have to take your knowledge of geometry and put that into an equation. So you come up with the equation based on what you know about the geometry. Then we just use algebra to solve it. So what we have here is they are congruent, which means their measures are equal. So I know then that ST, the measure of ST equals the measure of T. Do you guys agree with that? Yeah, that's what we just learned about congruency. So then I know that 3x plus 3 equals 2x plus 9. We came up with this equation. Now be careful. Just because there's 2 equations doesn't mean they automatically equal each other. You've got to look at what information they gave you, okay? All right, let's go and solve. What do we get for x? 6. Awesome. Very important that in geometry, the number 1 mistake people make the entire year is not answering the question. What does this say? Value ST. We found an x. So we're not done. If you stop there, you'd be only part way there. All right, so let's go and find ST. So 3 times 6 plus 3. So 18 plus 3, 21. Now, again, we're in high school. I trust that you can do some mental math. I would expect to see your setup of the equation with x equal to 6. But when you plug it in, I trust that you can plug that in and simplify in your head and have just s equals 21. I don't expect you to write this first step out. If you want to, that's fine. But or something as small as that aspect. All right, what's the value of TU then? 21. Did I have to plug it back in? No, you could if you want, but since they're congruent, it should be the exact same. Now again, do be careful because it might have asked you instead of TU, it might have said SU. What would be the value of SU? 42. Okay, so again, just make sure you're carefully reading the questions to know what your this means. Okay, let's go ahead and take a look down here for our numbers 9 through 13 with their multiple chunk over here. So it says if AD is 20, AC is 3x plus 4, find the value of x. Now again, they didn't tell me anything about the characteristics of the picture. We have to know that from our drawings. We have this here, so we have AD and DC are congruent. Awesome. So they gave us that AD was 20. And they gave us that AC was 3x plus 4. So what equation can I make based upon my picture and the information they gave me? There's a few different ways you could go about this. Okay. Good. Would you, so actually I think we might have done that back. So you said 2 times 20 3x plus 4 equals 20. Be careful. We want to go the other way. We want 20 was only half of it, right? So 2 times 20 would give us that. Good. So you could do that. You could double. We know AD is 20. So how much must the whole thing be? 40. So we could say 40 equals 3x plus 4. How else could I have set this up? Instead of doubling that 20. How else could we have set it up? Oh, I'm good at wait time, guys. I can wait as long as I need to. Feel free to talk to one another. How else do we set it up? Oh, yes, a brave soul, Tommy.
1.5x plus 2. Then 20.
Yeah. So if this is the whole thing, 3x plus 4, but we know 20 is just half of it, couldn't we say that the half of it equals half of the whole thing? And Tommy went ahead and did that half for us. He said 1.5x plus 20. Do you guys agree with that? Yeah. Do I care which way you do it? Nope. There are multiple ways to do it, whichever you feel most comfortable with. If I were to have this fraction, I would probably, at this point, I probably would leave it as 3/2 and then just multiply both sides by 2 because I don't like fractions if I don't have to work with them. But again, whatever you feel more comfortable with. Okay, so let's go ahead and find our value of x, whichever way you prefer. I'll let you guys solve and then tell me what you get. What do we get for x? Now again, make sure you're answering the question. Find the value of x. Sweet, we did that. But there's more. Then find AC and DC. How much is DC? 20, right? It's the exact same as AD. So we have that one pretty easily. DC equals 20. Now for AC, we could take 12 and plug it back into our expression for AC, or what is AC? 40. 40, yeah, it's just the 20 from the end. Good. For that now again, be careful. Here they gave us part of the segment instead of, so they gave me a part of a segment and then expression for the whole thing. So again, just make sure you're aware of what they give you to know how to set it up. All right. What do I want to go to next? I think it's 14 area where there's when we start having angles. Flip to the inside. Yeah, or 14, 15, 16, 17. All right, so lots of segmentation postulate. Also lots of angle addition postulate. And with angles, we have a little bit more, right? We know about linear pairs, we know about supplementary, we know about vertical angles, we have about right angle congruent. So there's a little more that can come into play here. We have angle bisector, all that. So let's go take a look at this chunk here, 14 through 17. So it's just let's use this picture here, and they give us a couple of angle measures. What else do we know from our picture? What is this notation here? They're congruent, right? Okay. Suppose they didn't draw that in for me. How would I have known that that was true if they didn't give that to me? Joseph?
Vertical angles, the theorem thing.
Yeah, the vertical angles theorem, yeah. And actually at this point I realized, I forgot to tell you guys, for vertical angles theorem, you'll see me use this abbreviation where I just say VA theorem. That's not Virginia theorem, vertical angles theorem. You are welcome to use that notation as well. We just use it a lot, and it's a lot faster to write that. I use THM to abbreviate theorem all the time. Okay, so the vertical angles theorem tells us that. So even if we didn't have it drawn in the picture, we ourselves would know that it's true. Okay, something I want you to be cautious of. So we see here this ray XH. Is ray XH an angle bisector for angle GXI? No, we don't know that it is, right? So do be careful. Don't trust the picture, just the information given to you on the picture. So if it looks like it's halfway, but they didn't tell you it's halfway, don't make that assumption, okay? So we don't know that that is truly cut in half, so just be careful with that. Okay, so what did they give us here? They said FXH. So this whole walking thing here is 130. Okay? And then FXG is 49. Alright, well if this is 49, how much must IXJ be?
49.
49, sweet. That was nice. Now, there are quite a few ways to find these remaining amounts. Let's go take a look at FXJ. I'll use my highlighter here. So FXJ. How can I find that amount? Can you do it?
Because it's the FXJ is supplementary to GXF. You can just subtract 180 degrees by 49 to figure it out.
Very good. So we're bringing into play here our supplementary angles and our linear pairs, right? So you could either say, hey, it's a linear pair with this angle over here, right? Those are linear pairs. Or you could have gone the other direction and said over here. But either way, linear pairs are supplementary, so 180 minus 49, what does that give us for this angle down here? Maybe it starts off with a 1.
31.
131, good. Sweet. Now, this whole thing here was 131. That is vertical angles with this entire thing. That's 131. Right now, that's not helpful for us, but it could be helpful later down the road. Okay. How would I find angle GXH? How much is angle GXH? We'll give you a couple minutes to do, or a minute to do some math there. Does it start with an 8?
Yeah.
Ends with a
1.
Good. Now what you just did is you applied the angle addition postulate. Right? We have FXG and GXH together give you the whole thing FXH. So you were using angle addition postulate. I'll just recognize it. Yes.
Wait, how did we get 131?
Down here?
Yeah.
So we know that this together is supplementary because they're a linear pair. So we just did 180 minus 49.
Whoa.
Does that make sense? Hold on. This one, sorry.
Yeah, I see.
Does that make sense? Alright, now last but not least, this little chunk over here. Again, quite a few ways to get there. We could talk about it in terms of supplementary angles. I know that 81 plus this unknown plus 49 must be 180. You could do 131, right? That's what this whole thing here would have to be. Subtract away your 81. Also, this is kind of getting ahead of ourselves, but how many degrees are there in a circle? 360. So you could add all those up and subtract from 260. That's probably the longest way. Technically, I didn't tell you that yet, but obviously you already know that from before. So what would our remaining angle here be? Go ahead, you get 50 degrees, good. Probably the easiest way is that it's these two angles together are vertical angle with 131, so subtract. Okay, so notice we applied quite a few different things. We've learned linear pair, supplementary angles, vertical angles theorem, all that together to get those different pieces of information. Now, what I want you to be careful with as you're answering the questions here is to notice whether they're asking for an angle or the actual measure. Number 14 says the angle FXG is congruent to what? When we're talking about congruent, we're talking about the picture, the figure. So I should be giving back another angle. For 15, it says the measure of angle GXH equals. We're talking about measures. They gave us numbers so we can find out the actual numerical value for it. So we should be given a number here. So 14, FXG is congruent to what angle? Good. IXJ or JXI, either way. And then 15, the measure of angle GXH would be 81. Okay, so notice that difference there. Questions with that? Let's continue on. I think I want you to go to the next page. Just more with angle addition postulate. Yes. Let's take a look at 28. So again, we're just dealing with angle addition postulate, all kinds of stuff we've learned. So 28 doesn't actually have any instructions in it. Let's take a look at the instructions for that section. So it says to solve for x and find angle measures. Okay. So they've given us angle AOB. AOB is 4x minus 1. EOC is 2x plus 15. And then AOC, that whole thing, is 8x plus 8. Oh, looky there. Maybe some angle addition postulate happening again. Would you agree that red and green equals the blue? Yes. Yeah. So it's just angle addition postulate. Once again, you have to use your geometry knowledge to set up your equation. So we recognize what we have here. Do I know that gray OB is an angle bisector here? They didn't give that to me, and it's not drawn on the picture. So don't make that assumption. Okay, so I have 4x minus 1 plus 2x plus 15 equals 8x plus 8. All right, I'll let you guys go ahead and solve. See what you get for x. And then go back and make sure you answer the question. Solve for x and find the angle measures. I made you talk to your shoulder partner a lot, so once you're done, I want you to turn to the person either in front or behind you, to someone other than your shoulder partner. Introduce yourself, and then share your answers so you guys see.
This person front or the time you use your shoulder partner?
Then talk to somebody else. Talk to someone other than your shoulder partner that's near you. If you need to team up with this like more than one person works together, that's 5. I'm just trying to get you to talk to somebody else and share your answers. And of course, you know, so the questions you have, any questions? Alright, I saw a lot of 3s for X. Do we agree with that? Is there anyone that needs me to go over that? Alright, so then did we get 12 for AOB? No. 11 for AOB?
Yeah.
Good. Don't forget to subtract that one. Do we get 20 for VOC? No. What do we get? 21. 3 times 2 is 6, not 5. You laugh, but that mistake happens a lot. What do we say? 21? Okay. And then AOC, you can throw it into that expression or just add them together, right? Awesome. Someone asked me last class if we need to have the degree symbol. Technically, yes, we should. I'm really bad about that. So I will not take off if you forget your degree symbol. In geometry, our only unit of measure that we use for angles is degrees. When you get to pre-calc, you will also use radians, so it's a little more important there. But we stick with degrees in here, so there's a degree. Okay. Questions with that? Let's take a look at, I think it's 32. Yeah, 32. So here they actually gave us some information in the prompt, but no picture. You get to draw the picture. Alright, so it says ray QS bisects angle PQR. Looks like we need an angle PQR. It doesn't matter how you draw a Q, obtuse, who cares, as long as it's angle PQR. So Q must be at my vertex, and then P and R are on the rays, and it could be either one. Alright. Ray QS bisects it. What does that mean if it's an angle bisector? It bisects it. Good, that's it. It's two congruent halves. So would you agree with this marking on the picture?
Yes.
Sweet. Okay, so that's how we're going to communicate to ourselves. Those are equal measures. Okay, so let's see what they gave us. They gave us, 32 is a little too easy. Okay, fine, we'll go with it. All right, so PQS is 3x. SQR is 5x minus 20. What do we know about these two expressions? They're equal. 3x equals 5x minus 20. Again, difference with geometry is you have to take that content and apply it so you know what equation you're in. All right, what do we get for x?
10.
Sweet. We're done. All right?
No.
What else does it ask for?
Measure
Of PQR. All right. Do we have any? We don't even have an equation for PQR. So how in the world are we going to find that out? Go ahead, Keegan.
Just solve for one of the angles, and since they're the exact same angle, you can just multiply that by 2.
Exactly. I'm going to go with my 3x angle. That's the easiest one, right? Throw in 10. I know PQS is 30. Since they're the same, 30 and 30 is
60.
60. Did I do my math right there?
Yeah.
Okay. Awesome. So technically x is 10 degrees and measure angle PQR is 6 degrees. We're not concerned about degrees. Alright, I want you guys to go try 34 for this one. Actually, do 33, 34, 35. Why not? So if you,
It's fine. It's fine.
that must be it. Again, use your shoulder partner, use those around you, raise your hand, let me know if you need help, I'll come around. You have me as a resource, you have those around you as a resource. Take advantage. As you're going through, go ahead and check your answers with those around you, so that way you can catch if you're making mistakes. I'm gonna throw up my equation setup in my S equals, so you can at least check to see how you did with that. And then of course the angle measurement would follow from there. Again, keep in mind that some of these you can do in a slightly different way, so you might have a different setup. You should still result in the same answer if your setup is. Are there any of these that we have questions on the setup for it? Or just questions about it?
So on 34, I ended up with the same answer as everyone around me. Oh, wait. We were solving for X.
Well, X and then we get PQR.
Okay, yeah, so I got PQR, I got the same PQR as everyone else, but I got X equals 14.
Yikes.
But I still got it right.
Interesting. What was your setup that you did?
I just did 3x minus 12 equals 30.
So what you're saying is that PQR, the whole thing, equaled PQS, half of it. You see that?
Yeah.
Okay, so fix that.
Yeah.
You just got lucky that your PQS is the same. Are there other questions? Okay, so again, keep in mind next class we do have our quiz 2 that's going to be over our geometry stuff, vocabulary, Euclid, segment and angle addition postulate. Yes. Nothing crazy. He is going to Does that sound reasonable?